On with second order differential equations and the characteristic solutions. Um, I want to discuss what happens when they happen to be complex, like P plus QI. I would say A plus BI, but I'm using A and B in my differential equation here. So let's say that this does have a solution and we find that y of t um, is equal to e to the P plus QI t. And notice it's plus or minus, but what happens with a minus is you just change the constant from a positive constant to a negative constant, so it's not a big deal. So if we have this solution where r is equal to this P plus QI, it looks like we're only getting one answer out of the deal, but again, there is that plus or minus, so technically it's 2. And what happens with the QI portion is actually kind of interesting. So if I break this down into a smaller piece, this would be y of t. And since the I is there, I'm going to give this a squiggly to designate that this is a complex function. And I really don't like working with complex functions, so I want to make sure that eventually when we get to the end, we're just going to have a y here. So if we do a little separation, this becomes e to the pt. And since it's adding in the exponent, we can change it to multiplication. So this would be times e to the qt, and I'm going to write I last, so qti. All right, so the piece that's giving me a problem is the second piece here, and there's a neat little theorem. It's called Euler's theorem. It's pronounced Euler's. I know it looks like Euler. And his theorem pretty much says that e to the I theta, a complex power, is equal to cosine of theta plus I sine of theta. And it's a neat little theorem, and it's easy enough to show. All you have to do is go back through and find the series expansion of e to the x. I think it's like 1 plus 1 over 2 factorial plus 2 over 3 factorial, something like that. And what you'll do is substitute in I theta, and what'll pop out is the series solution for cosine and the series solution for sine. That's going back into Calc 2 or 3. All right. So we can use this neat little theorem to break apart this QTI, where QT in this case is theta. So this becomes y bar t, or squiggly y squiggly, is equal to that, what we're used to, the pt. This is the normal rt. And then the e to the qti is going to become, well, I have to get the constants of integration in there. So c1 cosine of qt plus, I'm going to put the I first, I c2 of sine of qt. Okay, that's all well and good, except it's a complex solution, and I'd rather just talk about a solution without the imaginary part in there. So my next little piece is to prove that a complex solution is also a solution by itself. All right, so let's add a little page here. Let's say we were working with something simple. Say y double prime plus 9y is equal to 0. Now the solutions we're going to get out of this is r is equal to plus or minus 3i. After we set up the r squared plus 9 is equal to 0, this would be the two solutions. So that kind of implies that our complex solution is going to be c1 cosine of 3t, if we go to a function of t, plus, and then we get this I c2 sine of 3t. Now if we kind of go backwards, this could be considered y1, and this could be considered y2. And the sum of these are a solution, so individually there are solutions too. That superposition property or whatever it is. So what I'm going to do is, well, this whole piece is a solution. I'm wondering if the I really is involved in that calculation. So if we set up the linear operator on this thing, and we call y prime plus 9y L, in other words, L of y is equal to the second derivative plus 9 evaluated over y. It's usually written this way. So this becomes the second derivative of y and 9 times y. All right, if we do this linear operator, well, linear operators are, well, they behave in a linear fashion. I forget what that's called. Oh well. So if we do a linear operator on y tilde, what's going to happen is you're going to have, and we'll just call this whole thing c1 cosine of 3t y1. We're going to have a linear operator on y1 plus y2. And then there's that I in there. So it would be I, y2. Let's keep that I separate. Well, if it's a linear operator, you can separate it over some. So you get the linear operator on y1 plus the linear operator on I, y sub 2. It separates over addition. And also constants can pull through. So I is just a constant, so I can pull it through. And you get the linear operator of y1 plus I times the linear operator on y2. Now we know this thing is equal to 0. So let's just set it up that way. And I already know that since this is y1, that this piece here is already equal to 0 if I plug it into y double prime and y. So this one we know is equal to 0. So for this one to equal 0, then Ly2 has to equal 0. So that's just saying that y2 is also a solution of this differential equation without the I, which is kind of cool. So we can go back to this one, and we can kind of just say, well, I really don't need that I there. So y of t is going to equal e to the pt, c1 cosine of qt, plus c2 sine of qt. I guess another way of thinking about it is possible for c1 and c2 to be complex, and we just choose c2 so that when it goes I c2 it becomes a real number, and then we can call that, I guess, c3 if you really wanted to. It's another possible way of looking at it. But either way, we're getting rid of the idea that c1 and c2 are imaginary, and we get this nice solution. So if we ever get characteristic solutions of p plus qi, or 2 minus 3i, or 4 plus 5i, we can separate it into an e function for the real part of it, and then a cosine and a sine for the imaginary part of it. For example, let's say we have y double prime plus 4y prime plus 6y is equal to 0. So our characteristic would be r squared plus 4r plus 6 is equal to 0. And there are now factors of 6 that add up to 4. And what I'm going to do is complete the square. I find that much easier than quadratic formula, especially when the even number is in the middle here. And then move the 6 to the other side. So half of 4 is 2, square 2, and you add 4. And if you add 4 to the left, you have to add 4 to the right. So we're going to get r plus 2 all squared is equal to negative 2. And then when we square root, we're going to get r plus 2 is equal to plus or minus I square roots of 2. Square rooting both sides. And then subtract the 2 to the other side. So you get negative 2 plus or minus I square roots of 2. So when we write this as a solution, change colors here, we're going to get y of t is equal to, and then it'll be e to the real part of it. So in this case, e to the negative 2t. And then times the quantity, c1 cosine of, and then the square root of 2 becomes the other part. So it becomes, and I'm going to write it kind of backwards, t squared roots of 2. Just because square roots are funny that way. Plus c2 sine of t squared roots of 2. Yeah, get that last parenthesis in there. So that becomes the solution of this second order differential equation. Not bad.